Hello, welcome to Chapter 9, Introduction to Differential Equations. So what is a differential equation? It's basically an equation, so it's an algebraic expression that has an equal sign, but it also contains a function and its various derivatives. It could have the first derivative and the second derivative, or maybe just the first derivative. And here are some examples. dy dx equal to sine x, y prime equal to x over y squared plus 1, the second derivative of y with respect to x minus y equal to 0. These are all equations. They all have equal signs, but they also have derivatives and the function. Normally, when we study algebra and pre-calculus and we introduce a new type of equation, we usually start off with what does it mean for something or a value to be a solution to that equation, and then we also go forward and learn how to verify if that solution is actually a solution to the equation. And what is a solution to a differential equation? It's the function itself. And how would we verify or validate that that function is a solution to the differential equation? We would, like we normally do, substitute the value of the solution into the equation. Only for differential equations, you also have to substitute the values of the derivatives of your function in order to validate. So here we've got a process down here, step 1 and step 2, and it says move everything, how to validate that y equal to f of x is a solution to a differential equation. It says move everything on the differential equation over to the left-hand side so that it is equal to 0 on the right-hand side. That is not necessarily required. You don't have to do that. You can just deal with the equation itself and just substitute the values of the function and substitute the values of the derivative, because that's what's happening in the second step. It says take the needed derivatives, following derivatives involving in the problem, and show that the left-hand side equals 0, which is the right-hand side. So that is really the method. You just have to do step 2. You don't have to do step 1. So here we have an example. So let's do that. And this says 2 dp dt equal to negative p, and we are verifying that p equal to negative t over 2 is a solution, or determining if it is a solution to the differential equation. So we first have to take the derivative. So if p is equal to e to the minus 1/2 t, dp dt is equal to e to the minus 1/2 t, but then times the derivative of the inside. So we get minus 1/2 e to the negative 1/2 t. Next, we take a look at our equation, and we have does 2 dp dt equal negative p, and we substitute our values in. So I'm going to substitute dp dt, which is negative 1/2 times e to the minus 1/2 t. Does that equal minus, and I'm going to substitute my function value in here, e to the minus 1/2 t. I simplify, and I can see that 2 cancels with the 2, and I am left with minus e to the minus 1/2 t equal to minus e to the minus 1/2 t, and I say yes, so it is a solution. Here's another example. We've got y double prime plus y plus 1 equal to 0. Is y equal to sine x a solution? So I see that I should be calculating the second derivative, and the first derivative is cosine x. The second derivative is minus sine x, and in substituting my values, y prime plus y plus 1, does that equal 0? In substituting negative sine x, if I add sine x and plus 1 equal to 0? The negative sine x and the sine x go away. Does 1 equal 0? No. So conclusion, y equal to sine x is not a solution to the differential equation. Good. All right. And at times, the solution may require that the functions pass through a particular point. If you recall from Calculus 1, when we discussed antiderivatives, we discussed what was known as the initial value problem. And really, when you were solving initial value problems, you were already solving differential equations. So first, we would want to make sure that the point lies on the solution. So here we're still verifying, is this function passing through a particular point the solution to the differential equation. So I'm first going to establish here, does y1 equal 0 for y equal to the square root of 1 minus x squared. And here is a function that is y of x, right, is going to equal 0, right, or your y. So I have input value, or the output value of y is 0, and the input value of x is 1, and that is true. So it does lie on that, the point does lie on that function. Next, I'm going to verify if the equation, or if the function is a solution. And it will involve me taking a first derivative because we've got dy dx. So if y is equal to 1 minus x squared to the 1/2, then dy dx, just using that notation, since we're using that notation in the problem above, I'm going to do the chain rule, 1/2, 1 minus x squared to the minus 1/2, and then times the derivative of the inside, which is negative 2x. I'm going to simplify. I can cancel the 2, and I'm left with minus x over the square root of 1 minus x squared for dy dx. So now I'm going to check the equation, and we've got, does dy dx, is that equal to minus x over y? And so I'm going to substitute my value of dy dx, does minus x over 1 minus x squared, does that equal, and I'm not doing anything with the minus x, but I am going to substitute the value of y, and the value of y is the square root of 1 minus x squared, and I can say yes. So conclusion, yes it is. Yes, y equal to 1 minus x squared is the solution. Good. All right, so moving forward, what's a first order separable differential equation? Solving differential equations can be tricky business. Why are we studying differential equations? We find that when we want to model real-world situations, that oftentimes it involves a rate of change, and a rate of change is a derivative. So usually when we model real-world situations and we're translating that scenario into an algebraic expression, it oftentimes comes up with a differential equation. And when we work with equations and we want to solve our problems or make predictions, we learn to solve those equations. So here we go in our first type of differential equation, and that's known as the separable one. Normally when we are solving differential equations, we're going to end up taking an integral, and in most cases taking that integral is going to be an indefinite one. And remember, when you take indefinite integrals, you end up with a family of functions. And then further, when we sometimes we want to find a particular solution, one that passes through a particular point, then we can find the specific one among that family of functions that fits our model. So first off, usually you are finding a general solution, which is your family of functions, and the particular one is the initial value problem, the one that falls through. So first order means that the highest derivative in your equation is a first derivative. First derivative is the highest derivative in the equation. Okay. Separable means that we can actually, with the equation, we can separate the two variables that appear in the equation. So looking down below here, namely, given a differential equation, we can break it down so that dy dx equals gx times h of y. And if we were to separate our variables, keeping in mind that we always want those differentials dy and dx to be in the numerator. So in this particular example down here, if I wanted dx is in the denominator down here, and if I wanted to make it in the numerator, I would multiply on both sides of the equation. So I would get dy equal to g of x h of y dx, and then I know to put h of y on the other side, so then I would get dy over h of y equal to g of x dx, and then I would have completely separated both of the variables to to either side of the equations. And then our final step would be, in order to get to a solution to this differential equation, we would integrate both sides. So after separating the variables, integrate both sides. Good. And then solve for y, or solve for the function. So coming back to just this equation here, dy dx equal to g of x times h of y. I know, how do I spot what am I solving for? Am I solving for y or am I solving for x? And I'm always looking at the numerator, because with our notation for derivatives, we either do y prime, and so the function would be y. In dy dx, it would be taking the derivative with respect to x of y. So I know that y is going to be our solution to this differential equation. So integrate both sides, and then if you can, solve for y, if possible. If it's hard to solve for y, and sometimes that is the case, then you can always leave your solution in implicit form. Good. And let's try some. Good. So let's try find the general solution to the given differential equation, include a sketch of 5 members of the family of solutions. So I see dy dx equal to negative x over y. I'm first going to move the dx over so that I have both dy and dx in the numerators. So I know which side to put the y's on and which side to put the x's on. And then I want to multiply by y on both sides. And now I'm going to integrate. And in integrating, I get y squared over 2 plus c1 equal to negative x squared over 2 plus c2. And then if I'm going to solve for y, I want to be able to, I'm going to move the y squared over, or the c1 over to the other side. And since both c1 and c2 are arbitrary constants, if I take c2 minus c1, both are arbitrary constants, I'm going to get a new arbitrary constant, and we're really just looking at a family of functions. So I'm actually going to call this a c star. Oh, sorry about that. And I can write over here that c star equals C2 minus C1 if you want to. And I still have the y squared over 2 on the left-hand side. And if I'm moving forward to solve for y, I get y squared equal to 2 times that entire expression. And in moving that through, I get minus x squared plus 2c star. And I can actually rewrite the let c equal to c star, because an arbitrary constant times 2 is still an arbitrary constant. And then I can rearrange that and call that c minus x squared. And I can solve for y, and that's going to be plus or minus c minus x squared. And that is my family of solutions. And what do they look like? They look like half circles. So when the upper family of functions, this would be y equal to positive c minus x squared, and the ones below dotted would be y equal to negative c minus x squared. Good. All right. Let's do it again. This one is also quite simple. So I'm going to separate the variables, and I get dp equal to minus p dt. So making sure that my differentials dp and dt are in the numerator. And I know then I want to separate my variables p, so I'm going to be dividing by p on this side, and I get minus dt on this side. I'm next going to take the integral of both sides. And then I get ln of absolute value of p equal to minus t plus c. And if I solve for p, I can exponentiate. So I can raise this to have base e, and then this would be base e, and this would equal e to the minus t times e to the c. And I can say, let my c equal, or my c star equal e to the c. And so I would end up with p here equal to c star times e to the minus t. And that would be my solution to the differential equation. Up above, the ln of p equal to negative t plus c before exponentiating, that is the general solution to the differential equation. It's just not solved for p, and it is in implicit form.